All right. Well, I'm Tyler, like Ryan said. I've just finished my undergrad at Valparaiso University in meteorology, and I am an incoming master's student at Texas Tech. So I'm going to talk about vertical coordinate interpolation. That is the main portion of what I've been working on with MetPy for the summer. So a couple objectives that went too fast. There we go. We want to create a simple function for users to do interpolation from isobaric coordinates to isentropic coordinates, and also from sigma coordinates to isobaric coordinates. And I'll talk about what those coordinates are in a minute. Basically, we want to be able to change coordinate systems, specifically talking about the vertical coordinate within a coordinate system. So what coordinate systems are we talking about? Isobaric, isentropic, sigma p, sigma theta, hybrid sigma. These all have a few differences. The main difference is, again, that vertical coordinate. So isobaric coordinates are a coordinate system where pressure is the vertical coordinate. Pressure decreases as you go up in the atmosphere. You can find a certain pressure value that's constant across your domain and label that as a level in your vertical coordinate system. So this is commonly used in dynamic analysis for jet streams, mid-latitude cyclones, snowstorms, severe weather. It's probably the most commonly used coordinate system among forecasters. And for example, the 500 hectopascal surface is commonly used. That's roughly halfway up by mass in the atmosphere. You'll often plot height contours on that, so how high above a reference point is that pressure level found. Now, isobaric coordinates do have a couple of disadvantages. The primary one is that when you're in high terrain like out here, the pressure surface may be below the ground. For example, 850 hectopascals is commonly used, but that can't really be used too much out here because that's below the surface. Isentropic coordinates are coordinates where potential temperature or entropy, if you recall physics, is the vertical coordinate. I'm not going to get real far into what potential temperature actually is. It just know that it's related to entropy, it's related to energy, and the main important thing to know is that unsaturated air will flow on an isentropic surface, which means looking at a isentropic surface is a more realistic way of viewing airflow through the atmosphere. This is often used for winter forecasting, especially synoptic scale mid-latitude cyclone forecasting. And you'll commonly do both horizontal single surface maps and cross-section plots. So other coordinate systems, these would be what I'm referring to as terrain following coordinates. These are your sigma p, sigma theta, hybrid sigma. There's small differences between the two, but the important takeaway is that they follow the terrain as in this image. They're not going to ever intersect the ground, which is good if you're trying to do numerical calculations along a grid. You don't want your level to suddenly not be there because it's below the ground. Problem is, these aren't very intuitive or informative to forecasters, so you need to convert from sigma coordinates, terrain following coordinates, to something like isobaric or isentropic in post-processing in order for model data to really be very useful. So that's what we're trying to do. So first, the interpolation isentropic coordinates. Often you will get model data from the National Centers for Environmental Prediction and their archive, and that'll come in isobaric coordinates. And you might want to do an isentropic analysis like these images. So what we're going to do is assume that temperature is going to vary linearly with the log of pressure. This has there's a few studies that have looked at various methods of interpolating to isentropic coordinates. This assumption is found to be a reasonable compromise of accuracy versus computational cost. So we're going to find the potential temperature on each of the isobaric levels, but this is going to vary by horizontally on the level because we're not yet on a constant isentropic surface. Then we're going to find the index value where the new potential temperature surface would go if you were to insert it into a vertical slice of your current data. Basically, we're just going to find where it needs to go. And we're going to use a search sorted applied along the vertical axis to do that. And then we're going to use Newton-Raphson iteration to iterate down until the change in pressure is no longer greater than a threshold. And that'll allow us to find the pressure at an isentropic level, whereas before we had the potential temperature at a pressure level. Then we're going to linearly interpolate the additional variables that you might want to have in isentropic space, like moisture and wind. And then it'll all come back out, and then we can plot it. So here's an example of what you would have to do to modify your script to now plot isentropic levels instead of isobaric levels. It's a simple one-line, two-line addition. There's also a quantity called the Montgomery stream function, which I also will not get too far into. It's related to geostrophic wind flow, if you're familiar with geostrophic wind. And sometimes researchers especially would like to see this in isentropic space. So it's also a simple calculation, so we've added a function for that as well. So here's an example of the output. You get, this is a map of 296 Kelvin surface with pressure, wind, and relative humidity plotted. Over here, it's the same surface, but we've now contoured Montgomery stream function instead. And then the other thing that you can do is an isentropic cross-section. And all of these plots came out of examples that will be available both within the MetPy GitHub site and the Python gallery site. And I'll show this cross-section again in a minute. I have the actual interactive version. All right, sigma to isobaric. Basically, when you get data out in sigma coordinates, you're going to have pressure as one of your variables, but it's not going to be constant horizontally. It'll change as the model level follows the terrain and goes up and down. So what we're going to do is use that as an x-coordinate of what the data currently is and interpolate to a common set pressure level, such as that 500 hectopascal surface. That means we're going to need a one-dimensional log linear interpolation over the whatever dimension corresponds to the vertical dimension of our input data, which can be three-dimensional or larger. The problem that we end up running into is that existing packages with interpolation functions expect one-dimensional data for a one-dimensional interpolation. You can't just give it 3 dimensions and say do the interpolation over the second axis. So we're going to actually write that and include it in MetPy. So the first thing we have to do is convert all of our units and then get rid of them. Ryan had a talk at SciPy that some of you may have watched on YouTube talking about the issues with units, and in a lot of cases you have to just convert them and then get rid of them and attach them later. So that's what we're going to do here. The Pint library has a nice wrapper that will make sure that the X and XP are in the same units, and then drop the units off of them and put them back on at the end of the function. The other challenge we run into with interpolation is that we need to have everything in monotonically increasing order, which often data is not in monotonically increasing order. A lot of times what's more common with meteorological data sets is to get monotonically decreasing order because pressure is greater at the surface than aloft. So the best way to overcome that is to simply sort the data before you start, do all of your calculations, and then put the data back in whatever sort of format it was coming in. Then we're going to do a similar thing to before with the isentropics and find the insertion point where our new interpolated points would go if we were to insert them into the old data array, and just do a simple linear interpolation. What we get out is a one-dimensional interpolation along whatever axis the user specified. This can and has been implemented in functions such as the isentropic interpolation, the getLayer function, which Matt may talk about later, and some others. It also allows for a one-line interpolation from sigma to isobaric coordinates simply by inputting the pressure levels you want, the pressure array in sigma coordinates, and then the other variables in sigma coordinates, and which axis of the array corresponds to your vertical axis. And here's an example of the output that we get. I will also note that this exact data set I tested within WRF Python, and we got a very similar interpolation out of WRF Python, which uses Fortran code. So in conclusion, for this part of the presentation, we've added functionality for isobaric to isentropic interpolation, which has been a requested feature of MetPy. We've also added a generalized interpolation function that will do one-dimensional interpolation along whatever axis the user specifies. That then allows for sigma to isobaric interpolation, which is another requested feature in MetPy. All of the code as well as examples are available currently on the GitHub page and will be within the next stable release of MetPy. And that includes examples for isobaric to isentropic, sigma to isobaric, and an isentropic cross-section. Some future work, I'd like to add some greater flexibility for data types. It's fairly flexible now, but does make some assumptions as to the type of data you're putting in. For example, the interpolation function doesn't like it if you want to interpolate to a different point along your grid horizontally. You need to have a one-dimensional array of interpolation points. It would be nice to make that flexible so that it didn't matter what dimensions you gave it. It would just interpolate. And then the cross-section plot that I will show in a minute currently requires a lot of code, but is another commonly requested feature and something that a lot of users would want. So it would be nice to simplify that down and make it a little bit easier to create a basic cross-section. Now there's one other thing I have that I've been working on for an example, and this is the Miller composite. And what is the Miller composite? The Miller composite is a basically an idea of a way of analyzing a severe weather case where you take and plot a whole bunch of data on the same map. And then as the joke kind of goes, wherever it's too dark to see the map, that's where your outbreak is. But using MetPy and some modern graphics options through matplotlib, we're able to actually add transparency to all of these color shaded fields, as well as pick out things like jet axes for the 850, 500, and 300 hectopascal jet levels. And we can contour variables, allowing for an analysis that looks a little bit easier than doing it by hand. Is certainly faster than doing it by hand, although there are some drawbacks. There's less flexibility in exactly what you outline. Miller 1972 is the paper if you're interested in exactly where this came from. The one thing I will note on this is that you can see from the jet barbs that there's some nice vertical wind shear right in here. Lifted index is the red contours, that's a stability index, and we see fairly unstable air in this general area. That corresponds to dew points at the surface greater than 65 Fahrenheit, some cyclonic vorticity advection at 500 millibars, as well as surface low pressure, which is the yellow, and then you can just barely see this tan color, that's a dry slot, corresponding to an elevated mixed layer at 700. These are all things that you're looking for when you want to diagnose a severe weather outbreak. What day is this? This is the 2011 super outbreak, the day that Tuscaloosa, Alabama, among other places, were hit by tornadoes. So that's an example of some of the plotting stuff that you can do in MetPy. I think I have a couple minutes I can take any questions, and then we'll look at a cross-section example.
I have a question. I'm sure it's a new question, but I'm going to ask it anyway. With NetPy having some issues with units and unit conversions and not being able to work with units, would it be possible to take UD units and incorporate it into NetPy?
I have never used that, so I would have to punt that question to someone else.
But Steve, so UD units is a unit package that enables all sorts of unit conversions that we develop here at Unidata, and Steve maintains that package, and it does all that fantastic unit conversion stuff for you.
Does it have Python binding? It has a Python binding, but the difference is it's more about manually saying, I need to convert from this unit to this unit. We use Pint as a way to take numeric arrays and have unit information attached. The problem isn't inability to cope with units. The problem is that you have things that look like arrays until you go to try to use them with other scientific packages, and then it falls. It fails in amazing and interesting ways.
So it's not the unit manipulation, it's actually just carrying over the units in the string.
It's more like you're trying to take these Lego blocks and piece them together, and everything looks like it's just going to fit fine, and then you're off by like a little bit. You're trying to, yeah. It's something it's an ongoing challenge we're going to be working on further.
And that
a few years ago, there was a talk on all the unit packages that are available within Python. They're available within Python online somewhere. I think it's just a summary of all that's available.
That was 4 years old, but yeah, there were about 17 covered in the talk.
Any other questions?
Are these analysis functions available in any other meteorological package? And your results agree with
So I, at some point, will have to test against Genpack. It's hard to do that right now because we can't just read in the same data file to MetPy. And there's also challenges with installing Genpack on the system I'm using. I've tried to do that. But I have compared it to the one site online that I've been able to find isentropic analysis, which is the Tropical Tidbits site. And it does compare pretty well with that site. They're probably using some slightly different tolerances in their iteration, maybe a different iteration function. So they're not exact, but they're very close to within pressure, probably a couple millibars. Yes, they're picking out the same features. The lines are in a slightly different place.
We should say that the technique he outlined for doing the isentropic analysis is the same one employed within Genpack.
All right. I have a cross-section plot here. And first I'll talk a little bit about what this plot is actually showing. First we have on the x-axis here corresponds to this red line up here. You're getting a vertical two-dimensional slice through the atmosphere. So we have pressure on the y-axis, and then this is currently longitude along this line on the x-axis. The image nest is the same image that I showed as an example of the isentropic interpolation earlier. Same data case, same level. The red lines are potential temperature lines. The wind barbs are wind barbs. And then the color filling is relative humidity. And what's cool about this is that we can just change any of these sliders, adjust the number of sampling points, move the line a bit, make it more of a vertical north-south cross-section than east-west. And right now it runs a little slowly, but you can see it updates, and then we get a new cross-section. So what's really useful about this is if you don't know exactly where in the data is the best place to have a cross-section, you can just adjust it using sliders and click the button rather than typing in a whole bunch of lat-long points and changing it and going back and rerunning cells. So it makes it nice for trying to determine where the best, most informative cross-section would come from.
The feature there on the left almost looks like an anvil. Is that just a coincidence?
Yeah, that's what you're actually seeing, are you looking at kind of this?
Yeah.
That's this little dry air slot right up here.
And it's too good to
Yeah,
Yes, dry air.
it's dry air. You would actually see the reverse if it were going through something like a thunderstorm. But it's not a thunderstorm. This is a winter storm case from 1987. Yep.
And would this qualify as a meteorogram?
No. A meteogram is a single station in time.
Okay. And this is all accessing remote data, right?
Yes, this is pulling NAR reanalysis off of the Nomad server.
Even in my view, this is still hitting the.
Yes.
Pretty simple.
It pulls in all the data ahead of time, and then you run the cross-section plotter separately. So the
So
data's
it's
all
already local.
the data's already loaded locally.
So that was awful zip. That's pulling it across, yeah.
It helps having this machine.
Good. Live demo actually worked.
All right, if there are any other questions, I can take more questions. Yes.
Would you be able to, obviously you can add another widget to change color ramps or something like that if you wanted to go down
Certainly.
that line?
It's all contained within this long function here. And as long as I put the functionality to change it within this cell and then added an option here with another slider, you could certainly change this to whatever you wanted.
Or it doesn't have to be sliders. A widget toolkit for the notebook has
Could be a drop down.
Yeah, it could be a drop-down window.
anything you can think of being done on a web page.
It's there. Very cool.
HTML5 and JavaScript.
Yeah, I just think some people might have, colored line or something.
Yep.
Yeah, certainly you could change that to whatever you wanted.
Great. Looks good.
So if you had another 10 weeks to implement more things, what would you be excited about doing next in terms of these kind of analysis tools?
I think making this easier. There's a lot of code there that the users would have to either copy and paste and modify or write themselves. And I think this can be done too, because once the plot is set, it's kind of a similar thing that would be extended among other cases. That would be one. I would probably like to go and work on some more stuff involving wharf data, for instance. Trying to get that more easily analyzed and interpolated. And then there's some other little things here and there.
Another round of applause.
All right.